So in the previous video, we did some exploration, and what we found, and this is in general true, that E of x plus y, so the expected value of the sum of two discrete probability distributions, is equal to the expected value of x plus the expected value of y. Okay? Now, we also had that the variance of x plus y is equal to the variance of x plus the variance of y. Now, within this, we considered that we had to have independence. Okay? Now, in the case of the expected value of x plus y, right, when we were thinking about independence, we were assuming independence in order to calculate the probabilities that were in the table. Okay, so what we did was we had a table, a sample space essentially, that you could build up with all of the r values for x along the top, all the r values for y along the bottom, and then we could work out the values that were going to be inside when we added the two x's and y's together. And then we had to build the probability distribution from that. Okay? Now, in order to work out the probabilities, we multiplied the probabilities of x and y's together. Now, in order to produce that, those two properties don't have to be independent. So x and y don't have to be independent in order to work out those individual probabilities. In the case that we were looking at, they did, okay, in order for me to be able to calculate them, but they wouldn't have to be independent to calculate those probabilities. Okay, so the consequence is, and as we'll see, is that this top one, it doesn't need x and y to be independent for that to be true. However, we do need this one to have x and y to be independent to be true. So this one only works if x and y are independent, whereas this one doesn't need the independence to be there. Now, what I'm going to do next is I'm going to go through a way of proving this statement here, which is definitely beyond the specification, okay? Just so you can kind of, you know, if you are interested, you can then see, right, okay, so that's how you can prove it. And then I'm going to prove this one as well, and that's going to bring in the independence, and you'll see, okay? So, first of all, let's take a look at that first one. So, you know, if you want to, you can stop the video now and move on. But if you're interested in seeing how we can derive these, then stick with me. Okay, so what I want you to do is think back to the previous video and what we did, because that's essentially what I'm going to build here. Okay, so imagine that you have a distribution for x where you've got these r values, which can be x1, x2, x3, etc. So let's just go up to x2, and it goes up to xn. And we have the probability of x being equal to xi. Okay, now you could write that as r if you like, okay? X is equal to r, but what I'm going to do is I'm going to just rewrite that as xi and xi there. And each of these will have a probability. So this will be the probability of x1. This will be the probability of x2. This will be the probability of xn. Okay? So I'm going to have one of each. So I'm going to have one for the y's as well. Let's use a different letter here. So yj. We're going to have the probability of capital Y being yj. And then we can have y1, y2, yn. Now, just for purposes, I mean, we could have that as ym, couldn't we? It doesn't have to be that they have the same number of items. Then we've got py1, So probability of y1, probability of y2, etc. up to the probability of ym. Okay, so here are our two discrete distributions. Now what I could do is I could then write that in a table. So just like we did before, where we would have each of the x's, so we'd have x1, x2, all the way up to xn on the rows, the columns rather, and then the rows y1, y2, ym. Okay, so in my table, rather than showing just x1 plus y1, I'm going to populate it with the probabilities of those occurring. So now, if they were independent, then the probability of getting x1 plus y1 would be p of x1 times p of y1. Okay? But we don't have to have them as independent. It could be that they're not independent. Either way, there is some probability of getting x1 and y1. And I'll write it like that. So this would be the probability of getting x1 and y2. Up to the probability of getting x1, ym. This would be the probability of getting x2, y1. This would be the probability of getting x2, y2. This would be the probability of getting x2, ym. So this would be the probability of getting xn, y1. And this would be the probability of getting xn, y2. Okay, and this would be the probability of getting xn, ym. So we've got this big table that we have here, okay, of all our probabilities. Now, over here, okay, so if I were to add all of those together, so p of x1, y1, p of x2, y1, p of x3, y1, etc., all the way up to p of xn, y1, that would be the same as having the probability of y1. Okay, all of those would add up to probability of y1 because all of your probabilities, the x1s, x2s, they would all add up to 1. Okay, so that in total would be the probability of y1. Okay, so if you had a total column here, so this would be the probability of your y's that you've got here. So that's your probability of y1. So if you want to write it as this, so y equals yj, that's what it would look like. So that, all those together, would add up to be the probability of y2, and so on, all the way down to the probability of ym. And if you had added all those together, then you would get the probability of x1. So we could have a totals row, and this would be the probability of your x's being xi. So all those together would add up to be the probability of x2, and all those would add up to be the probability of xn, and all of those and all of those would add up to be, of course, 1. So all of those would add up to be 1, and all of those would add up to be 1. Okay? So this essentially shows you all the probabilities that we're dealing with. Now, okay, so that might seem quite, going over your head at that point, but that's essentially we're dealing with all possible scenarios here. So how do you work out E of x plus y? Right, I'm just going to get rid of this now. I don't think we need that anymore. So how do we work out this? Well, what we would need to do is we would need to add together each of the x's with the y's, and they would then need to be multiplied by their respective probabilities. This is kind of like, when we have our just a regular table, a probability distribution table, we've got the R's and the probabilities. We just multiply those together and add them together. So we do the sum of each of the R values times by their probabilities. Okay, that's what we do. So here we need to sum together all of the xi's and yj's. So give myself a bit more space. So I need to add together all the xy's and yj's and multiply them by their respective probabilities. This is kind of like, instead of just having a one-line table, this is a two-way table. So I need to sum together all these possible combinations and multiply them by their probabilities. So xi, y, j. Now, because you've got i's and j's in this, when I add them all together using the summation, I actually need a double summation because I'm dealing with i's and j's at the same time. So essentially I need one for i's and one for j's. Okay, right, keep with me here, okay. Now, when I can multiply that out, okay, using the regular regular way of how summations work. So I could write that as xi times the probability of xi, yj, the comma, plus double summation ij of yj times the probability of xi, yj. Let's get rid of that. Now, the xi here has got nothing to do with j. So I can pull that xi out of the summation to do with j. So I just have the summation of I times xi times by the summation of for j's of the probability of xi, yj. And likewise here, I can keep with the, because I've got the yj there, so I can't really pull that out. But what I could do is I could just reverse the summation symbols that I've got there. So this isn't, I'm not cheating. Just so you know, I'm not cheating here, but I'm going to just reverse the symbols, and that's perfectly fine because it didn't matter which order I put the i's and j's in there. That's perfectly fine because they're all going to get added together anyway. Everything's going to get added together and multiplied by each other anyway. So it doesn't matter actually which way round I put the i's and j's. So the yj can come through. And then I can have the summation of the i's of the probability of xi, yj. Now, if I add up all of these with respect to the j's, okay, that means I'm adding up all the y's. So I'm getting xi, y1, xi, y2, xi, y3, xi, y4. So it's these, x1, y1, xy, it's all of these columns rather. So that column there, for example, p of x1, or p of x2, or p of x3, that's what we're going to be left with. We're actually going to be left with p of xi here. So that is the sum by xi of p of xi. So it's all the y's are being added up Okay, so that's essentially adding up a general column. Now over here, we've got the summation of the yj's, and this is adding up all the i's. So we're getting x1, x2, x3, and so on. So we're getting x1, y1, plus x2, y2. Sorry, x1, y1, plus x2, y1, plus x3, y1, etc. So it is a general row. That one's staying the same as yj. That one is changing. That one's getting added together. So we're actually looking at one of the rows. And so in general, that is a pyj. So what I've got here is the summation of the x's times by the probability of x being equal to xi. And here is the summation of the y's being multiplied by the probabilities of y equaling the y's. That is E of x. That is E of y. And so that proves that that is equal to that. It is quite a heavy proof, okay? Especially with the amount of notation, new notation with the double summations that you've got to deal with there, okay? So, you know, it's quite nice to see, but well done, you know, if you followed that working through, okay? So good work if you did. So let's now, we've proved that result, and within it we didn't require independence, okay? Because at no point did I require it. You could assume it's independent if you've got two just random discrete probability distributions. In order to multiply the probabilities together, you would have to, if you couldn't work it out in another way. But these probabilities do not need to be independent for each of them. There was nothing saying that they had to be, okay? So, I think you'll probably find the next proof more straightforward, because now I can utilise that result there, okay? So we're going to start off by with the var of x plus y. Now, we know what var of x is, so we should be able to write that as e of x plus y squared, take away e of x plus y squared. Okay? Now what I'll do is I'll expand that bracket out, so we get x squared plus 2xy plus y squared. And here I can rewrite e of x plus y as e of x plus e of y. Now using this can be extended so that now I can split that up as e of x squared plus e of 2xy. Now e of 2xy can also be written as 2 lots of e of xy. You can also prove that relatively easily. Plus e of y squared. So I can split that up into that. And here I'm going to have e of x squared. I'm going to get, so 2 lots of ex, ey. So take away 2 lots of ex, ey. And take away an e of y squared. Now, the bit that comes into question is here, e of xy. Now, if x and y are independent, then E of xy is equal to E of x times E of y. Okay, so that is the case that brings in the independence. Okay, and why we need x and y to be independent in order for this to be true. So we get this so assume x and y are independent. We need that to be the case. Plus E of y squared, take away E of x squared, take away two lots of E of x, E of y, take away E of y squared. So this term cancels with that term, and I have E of x squared take away E of x squared, so I've got those two terms, plus E of y squared take away E of y squared. So those two terms. And of course that is var of x, and that is var of y. Okay, and so we need to have x and y independent for this second one, but you don't need it for the first one.